Hope everyone was expecting me and not Alex. So thank you to those who anonymously sent feedback through the system. So what I understand is that the first class was the correct pace, and yesterday was a bit too fast. So today is going to try and go a little bit slower than yesterday. Please help me as much as you can by telling me when you don't understand. Okay? And I'll try and slow down to the correct pace. Okay? So even though we're going to be talking about some slightly more advanced things today, we'll try and do it nice and slowly. We just get as far as we get. Okay? There's no rush. Okay. Okay, great. So we saw yesterday and then this morning in Jin Young's talk about the idea of a threshold. So the definition of a threshold is, so PC is a threshold for a property of graphs G. By a property of graphs, I just mean a collection of graphs. I'll maybe assume that the graphs are sort of, they're symmetric, so, but you will not worry too much. If probability that GMP is in G tends to 0 or 1 if P is much smaller than PC or if P is much bigger than PC. And PC is a function of n, right? So okay, so if such a function exists, we call it a threshold. And the sort of magical thing is that for any property which is increasing, which means if you add in more edges, it doesn't become false, then there exists a threshold. This was proved by Bolobash and Thomason almost 40 years ago. The proof is it's not too difficult, but I'm not gonna do it. I'm not gonna say anything about it. So it's a very simple argument using something called sprinkling. You sort of throw in lots of copies of independent copies of GMP, and it falls out. Anyway, so we saw yesterday, just for example, e.g., 1 over n is the threshold, perhaps I'll say, the threshold for the event that you contain a triangle. Okay, so the family of all graphs that contain a triangle, that's a property of graphs, and has threshold 1 over n. If P is much smaller than 1 over n, with high probability you don't contain a triangle. If much bigger, with high probability you do. Okay, that's what we saw yesterday, and also Jin Young talked about this morning. So I'll do one more practice threshold problem, which is on the example sheet. So what is the threshold for the property of being connected? So if you were paying attention to Jin Young's talk, you'll know it's up to a log factor the same as the expectation threshold. But let's not worry about that. Let's just think about this particular problem. Okay, so who can give me a bound, either from above or from below, some idea, like what do we think this threshold is? How big does P have to be before GMP is likely to be connected? So another way of saying it, for which functions P of n is GMP likely to be connected. Okay, how could we even approach this question?
For a lower bound, I think it's a lower bound. You can try to find the value of p where it's expected to have n minus 1 edges.
Right, this seems like a good idea. So we can look for what Jin-Young calls the first moment obstructions. We can look for properties that you need and then just count the expected number of such things. So observation idea 1, we need at least n minus 1 edges to be connected. Right? The first things you learn in graph theory, perhaps. Certainly if you learn from the combinatorial book. Okay, so you need at least n minus 1 edges. If you're connected to graph on n vertices, you have at least n minus 1 edges. So if you let x be the number of edges of GMP, well, the expectation of x is, so each edge is present with property p, there are n choose 2 edges. So if this is much, much smaller than n, this implies, so here perhaps, the probability that x is at least n minus 1 is at most what? Let's remember what we learnt yesterday. What should we use? Which inequality should we use here? Markov, right? And so most the expectation of x divided by n minus 1. If the expectation is much smaller than n, this tends to 0. And this holds if and only if p is much smaller than 1 over n. Right? So if p is much smaller than 1 over n, the expected number of edges is much smaller than n. So by Markov, I'll write Markov and Chebyshев over here perhaps. I'll stick them in a corner somewhere. Markov says probability that x is at least t is the most expectation of x over t. And I'll write Chebyshev when we need it. Right? So by Markov, this probability tends to 0. So with high probability, we're not connected. Great. So we have a lower bound of 1 over n. OK. What about an upper bound? How are we going to show that GMP is connected if p is big? So now we're for an upper bound, we're going to say, OK, when it says unlikely that GMP is not connected, we say if GMP is not connected, then, okay, what does it mean to be connected? It means between any 2 vertices, you have a path between those 2 vertices. Okay, that doesn't sound very useful. Okay, what's another characterization of connected graphs? Yeah, exactly. If you're not connected, then you can partition the vertices into 2 pieces, A and A complement, such that there are no edges between them. Right? There exists a set A such that there are no edges between A and A complement. Okay. So what should we do? Yeah, count these things. Exactly. Do what we do every single time. We define a random variable. X is the number of sets A such that the number of edges between, there are no edges between A and A complement. Bound the expectation. What is the expectation? You can just write it down. What is the expected number of sets with this property? Well, we have to sum over all sets A of, what's the probability of this event? Probability that there are no edges. Okay, maybe I'll come way back over here. Okay, what is this probability?
1 minus p to the power n minus the size of the x.
Yeah, exactly. So for every pair with a vertex in A and a vertex not in A, it needs to not be present. Happens probably 1 minus p. They're all independent. So 1 minus p to the power, the number of edges between A and A complement. So sum over A, 1 minus p to the size of A times n minus size of A. Okay, so it only depends on the size of A. So we can write this as the sum over k, 1 minus p to the k times n minus k. Times the number of sets of size k, which is n choose k. And just one little observation. Which values of k do we need to cover? K goes from where to where? What's the smallest set we need to worry about?
1.
Size 1. Size 0 we don't need to worry about, right? It doesn't count. And what's the largest we have to worry about? N over 2. Thank you. Exactly. We can always take the A to be the smaller one. Great. So we've got some sum. And we know how to bound sums like this, right? We already have these tricks from last time that we bound 1 minus p by e to the minus p, and we bound n choose k by en over k to the k, right? So using our standard inequalities, we can bound this thing by sum over k of en over k. I'm going to pull out this factor of k in the power times e to the minus p n minus k to the k. And our question is now just when does this tend to 0? Right? How big do we need to take p before this thing tends to 0? Right? If it tends to 0, then with high probability, then the expected number of such things is small. So by Markov, with high probability, there are none of them. Okay? Okay, so this is a slightly weird expression, but it's not so difficult to deal with. So look, we got it. P appears here only. Right? Here's your P. So it's like e to the minus p times something between n and n over 2. So we want p times n to be big enough to beat this n over k. Right? So how big does p times n have to be? Like log n. So if p is bigger than, let's say, 3 log n over n, then e to the minus p n minus k, I'm going to put 4, just to make my life a little bit easier here, is less than 1 over n squared. Right? Because k is almost n over 2. Right? So e to the minus p n over 2, e to the minus 2 log n is 1 over n squared. Okay, now plug in here, that easily beats this n. What do we get? So therefore, the expectation of x is at most the sum over k of 1 over n to the k, which tends to 0. Right, as n tends to infinity. Okay, I was not very careful here. If you're much more careful, you can get rid of this factor of 4. Well, let's not worry about it today. Is it okay? Okay, so what have we proved? this implies the probability GMP is not connected which is at most the probability that x is at least 1, right? If GMP is not connected, then x is at least 1, right? That's this inequality, which is at most the expectation of x by Markov, which tends to 0. So we've shown the threshold is at most log n over n. Right? Do not look at all happy. So you should definitely tell me when I'm going too fast. Because otherwise I'm going to think I'm going too slowly and speed up. Go ahead.
It's not clear for me.
Yeah.
How do you get the expectation of x is greater or equal to?
This guy.
Yes.
Right. Were you okay with this calculation?
Yes.
Right, so I'm just plugging in here the bounds. This thing is at most 1 over n squared. So if you put here 1 over n squared, that kills this n. Okay, so maybe I'm cheating slightly here. Maybe it's like e over n squared or something. K is at least 1. Yeah, so let me put an e here to be really correct. Yeah. But really, all I need is anything that goes to 0. Right? Yeah, thank you. More questions, please, yeah.
I think I recall in the first presentation
Yeah.
this was also the threshold for containing Hamilton cycle.
Yes,
Okay, so it is the same.
it's the same, yeah. Yeah, so that's why I wanted to show you, because proving it for the Hamilton cycle is actually quite difficult. That, yeah, I would do it in maybe a second course in combinatorics, not counting this as a first one, like 2 semesters of combinatorics, there may be. Probabilistic combinatorics. Whereas this then is relatively easy. So yeah, it's the same threshold for sort of the same reason, but the proof here is easier. Yeah. More questions? Okay. So we have bounds on the threshold. What have we proved so far? Here we proved a lower bound of 1 over n, with an upper bound of log n over n. So which one is correct? Over here, maybe. No space. We'll put it here. So. Right? So we did this nice, simple first moment calculation, counting edges to get the lower bound. And we did this other first moment calculation, counting pairs with no edges between them to get the upper bound. And, okay, you already guessed what the right answer is. The right answer is the upper bound. So we need to improve this lower bound, just by a factor of log n. So why was this argument that I just erased, why was it weak? So you throw in these n edges randomly, but you're not connected. Why are you not connected? What's the most likely way to not be connected? And I think you can sort of see it in this calculation as well. Where was the bottleneck in this calculation? Why do we really need this log n factor in this calculation? Say it loud, sorry? K equal to 1, right? That was the worst case. As k got bigger, our lives just got better, right? We had this power of k helping us, and also we had this k down here helping us. So the worst case of all is k equals 1. What does k equals 1 correspond to? An isolated vertex. So what this is hinting to us to do is say, look, if you just throw in n edges, or 100 n edges, Most places you're okay, but somewhere, maybe you just don't put any edges there. Okay, so let's try to count. So idea 3, show that if p is much smaller than log n over n, there exists an isolated vertex. Okay, let's try to do this. So, what should we do? Of course, we should count isolated vertices, right? X equals the number of isolated vertices in GMP. Okay. What is the expectation of X? I'm going to do the expectation here. What's the expectation of X? Sum over vertices, probability isolated. I'm not going to have space here, am I? No, I'll do it. V, probability V isolated, which equals, what's the probability of vertex isolated? 1 minus p to the n minus 1. N times 1 minus p to the n minus 1. How large is this? As always, 1 minus p approximated by e to the minus p. This is approximately n times e to the minus pn. When is this thing 1? Well, it's equal to 1 if p equals log n over n. Right? The solution to this equals 1 is pn is log n. Right? Okay, so this is the point at which, is log n over n is the point, exactly the point at which the expected number of isolated vertices gets big or small. Okay, so what do you want to do? We want to prove, so claim, or lemma if you like, if p is much smaller than log n over n, maybe I'll just say is less than this over 2, then with high probability, GMP has no isolated vertex. And what did we just prove? We proved that for this x, the expectation of x, we would like this to be small for this value of p. What was I saying? Sorry. Has an isolated vertex. Apologies. Yeah, please tell me when I make silly mistakes. It helps, yeah, apart from helping me correct them, it also lets me know that you spotted them. Right? Don't sit there quietly having spotted them. Okay. If p is small, we want to say you do have an isolated vertex, therefore you're not connected. So we would like this thing to be big. Okay, and this thing is equal to this. Which is, right, so there's not exactly, this is actually an upper bound, but it's a very good upper bound. So if we give ourselves a factor of 2 here, then this definitely goes to infinity. Right, this is very close to e to the minus p, definitely within a factor of 2, and so if p is much smaller, then this n wins easily. Okay? Yeah. Now, there are some like little bits of analysis that come up all the time in probabilistic combinatorics, like this, so it's good to just try and get used to them. It's just a bit of practice. Right? Okay, so are we happy? The expectation's large, so we won. Right, thank you, exactly, right? It's not enough to show the expectation is large, right? We saw this yesterday, okay? If we want to show that actually x is large, we need to bound the second moment. Okay, we need to use Chebyshev, which tells us the probability that x is close to its or far from its expectation is small as long as the variance is small. Right? So we need to show the variance is much smaller than the expectation squared. Excuse me. Right? Okay. So we need to bound the expectation of x squared. Do you want me to remind you about this? You're happy? It's okay. Anytime you want me to remind you of something, then you should just yell. Okay, so how do we calculate this expectation squared of x squared? What is it equal to? Yeah, exactly. This is the sum over one vertex, that vertex isolated. You do the sum over two vertices, pairs of vertices, that they're both isolated. Oops. Right. And what is this probability? There's, so u and v could be the same as each other, in which case this is just the expectation. You always get this term from taking the two the same. Plus, if they're different, you've got n choose two choices, 1 minus p to the power. Let me maybe do it over here. So u is isolated means none of these edges are present. And v is isolated means none of these edges are present. This one we already have. Okay, so these events are not independent. They depend on each other, but in this very weak way. It's just one of these non-edges helps us. And as a general rule, if you have very weakly dependent your sort of sum of very weakly dependent random variables, the second moment is likely to be small. Right? So you're likely to have concentration when you're summing up things that are almost independent. And you see it here. So how many non-edges we need? We need n minus 1 plus n minus 1 minus the one we counted twice, 2n minus 3. Yeah, perhaps I won't do this, this full calculation, but so from here you can very easily prove the variance is small, apply Chebyshev, and you get this result. Okay, maybe I'll leave that last part as an exercise to avoid doing too many calculations on the board. Okay, so what did we just prove? We just proved the threshold is log n over n. Okay, so you saw, like in Jin Young's talk, this log factor, the difference between the expectation threshold and the real threshold, they can differ by a factor of log n, and here's the first example of that. Right? And the reason is there's this local obstruction to the property. So when we were counting edges, that was a global obstruction, and that gave the expectation threshold. But here we have a different thing. We have this local obstruction. Okay? And that's what gives you this extra log factor. And this turns out to be something that happens universally across properties of random graphs. This is what the Kahnke-Lie conjecture, the one that Jin talked about, that they proved, and also the one they're trying to prove. Both of these are saying that. They're saying this very general version of this simple fact we see in this problem. Okay? Okay. Great. Okay, so that's all I want to say about thresholds right now. Sorry?
Could we just get a lower bound for having an isolated just by summing the probabilities and subtracting the probabilities that two of them happen together?
Yeah, so that will give you a lower bound, but what lower bound will it give you?
Those values and I guess it also could work. Yeah?
So I think that the problem is, when the expected number is large, the number of pairs will be larger than the number of single guys. So when you subtract off in this inclusion-exclusion, you'll actually get something less than 0. Yeah.
The probability that two of them are
The expected,
isolated at the same time?
it's basically the product, but the expectation of x squared is bigger than the expectation of x. So, I mean, you see it here, right? The number of pairs is number you get, number of single guys plus something. And so if you subtract them off, if you just do inclusion-exclusion, then you'll end up with nothing. Yeah, yeah. So yeah, it's a natural thing to try, but yeah, in this case, it doesn't work. Yeah. Yeah, I mean, this is the basis of sieve methods in number theory, right? That a lot of sieve methods are based on just this inclusion-exclusion. And so sometimes it works, but
If I'm right, the current constant is exactly 1, yes?
yes,
How is the proof of that?
exactly this. Just calculate more carefully. Yeah, so if you just do exactly so, exercise, take this proof, calculate carefully, and prove you get an extremely sharp threshold. So in fact, what we proved, if we were just a little more careful, would be probability that GMP is connected tends to 0, 1 if p is less than log n minus omega, or so let's take omega lambda over n, or p is bigger than log n plus lambda over n. This is for any lambda tending to infinity. So really, you only need log n plus some large constant or minus some large constant. Right, this is the window in which this event is happening. And if you really want to challenge, then you can worry about what happens when lambda is constant, when the answer is e to the minus lambda or something. And I think that maybe doesn't follow from this, but yeah, there's more of a challenge. So yeah, but this was all proved by Edish and Rainey in their very first paper, I think, on, or maybe their second paper on in 59 or something, on random graphs. They're one of the first properties that they looked at.
So when it's exactly log n over n, the probability is sometimes
Sorry? So the threshold is really exactly log n over n plus some smaller order term.
No.
Yeah.
I'm asking what happens if p is exactly
Log n.
over n.
So your probability of being connected is almost the same as being the probability of having no isolated vertex. The number of isolated vertices is a Poisson random variable with this mean. And so the probability is very close to the probability that a Poisson random variable with that mean is 0 or non-zero. Yeah, so something even stronger is true. If instead of taking GMP, you just add edges randomly one by one, then with high probability, the edge that makes you connected is the edge that hits the last isolated vertex. So you finally throw in one edge that kills the last isolated vertex. With high probability, that's the edge that makes you connected. It's called a hitting time result, so this even stronger version is true. They're really almost the same thing. Everything else can go wrong is less likely. Yeah, we're just seeing sort of from a little far away, right? But if you calculate more carefully, then that's not so easy to prove. That takes more ideas. Yeah. But just with this proof, just with exactly what we did, and a slightly more careful calculation, you can prove this. Yeah, so I was planning to prove this, but then I saw your faces and decided not to. Yeah. Are there more questions about this? Please.
Here in the previous talk, we usually look at when B is much larger or much smaller than something. What happens when you get close to that?
Yes, so very good question. Right, so this idea of a threshold was if you're much bigger or much smaller. and there's always a threshold. This is a much more precise thing. This is called a sharp threshold. And inside, in between these two functions, is called the critical window. Inside the critical window, then there are very interesting questions to ask. So for example, here's a question, not this one, but that we haven't been able to answer yet. So if P equals, say, some constant over n, what is the probability that G and P contains a triangle? Right? This is what we haven't answered yet. So based on what we've done so far, you can show, with some work, that this is not close to 1 and not close to 0. It's something in between. What I'm hoping to do, maybe even today, but maybe there won't be time, is to determine the correct function for this behavior. So to do that, we'll need to prove what are called the Janssen inequalities. That takes a little bit of time. Maybe there won't be time today. So maybe tomorrow. Yeah, so perhaps, yeah, we'll have to decide exactly what to do tomorrow. But yeah, so there's these are interesting questions that require more advanced techniques that, yeah, are right at the borderline of what we might cover in this course. Yeah. Okay. More questions? Okay. So, yeah, should I do this instead? I was going to give you one more fun example, application. Yeah, maybe that's better. And then we'll come back and maybe try to think about this afterwards. So here's the next problem. I don't know what number it is, like 12 or something. So I want to talk about size Ramsey numbers. Yeah, probably this will take the rest of today, and then tomorrow we'll do the other stuff. Okay, so what is the size Ramsey number of a graph? This is the minimum number of edges in a graph such that G arrows H. So I'm introducing some new notation, which you'll see on the example sheet. So G arrows H means that for every coloring of the edges of G, red and blue, there exists a monochromatic copy of H. Okay, so instead of coloring the edges of the complete graph now, we're coloring the edges of any graph. We get to choose the graph. Okay? We get to choose the graph. It should have lots of copies of H, of course. So we have a chance of finding H. Whenever we color, we're going to find a monochromatic copy. Okay, so to warm up, let's think about the Ramsey number of the clique. So question, what is the Ramsey number of KK? The size Ramsey number. Okay. Can you give me a bound, an upper or a lower bound?
Ramsey number 2.
Thank you. So the size Ramsey number is at most the Ramsey number of K, choose 2, and the proof, take G to be the complete graph with Ramsey number vertices. Right? Okay, that graph definitely works by the definition of the Ramsey number. Okay? We don't know what the Ramsey number is, but whatever it is, that graph works. Okay, so theorem. Actually, the size Ramsey number of the clique is equal to the Ramsey number choose 2. Okay, so this theorem says you cannot do any better. the best thing you can do is just take a clique on enough vertices. How do you prove this? Has anyone seen this before, by the way? Okay. If you've seen before, then you can keep quiet for a minute. Okay. Okay. So I'm going to give you a clue. I think this is not easy to see, but here is a big clue. We're going to prove a lemma that says the following. The number of edges of a graph is at least the chromatic number of that graph, choose 2. For any graph G. Why is this lemma true? Yeah, right. So take a proper coloring with chromatic number of G colors. Between any two parts, there must be at least one edge. Otherwise, you could merge the two parts and have a proper coloring with fewer colors. Right? So it's just immediate from the definition. Right? Proof. Take a proper coloring. With chi of G colors. Must have at least one edge between any pair of parts. Right? If there's no edge between these two, then just use the same color for both. Right? Contradiction. Okay. That was a weird hint, right? But why are we now done? Yeah, exactly. So, take any graph with fewer than this many edges. Prove if E of G is smaller than R of K, choose 2, then, by the lemma, the chromatic number of G is smaller than R of K. What does that mean? That means you can properly color the vertices with Ramsey number of K, fewer than Ramsey number of K colors. Okay. And we know, by the definition of the Ramsey number, that if you have fewer than this many vertices, there's a red-blue coloring with no monochromatic KK. Take that coloring and blow it up. Right? Replace each vertex with one of the parts of the coloring of G. Does it make sense or not? I'll draw a picture. I should draw a picture. So if, let's say, M is less than R of K, implies that there exists a coloring of the edges of the complete graph with M vertices, red, blue, with no monochromatic copy of KK. Right? This is the definition of the Ramsey number. Right? The Ramsey number is the smallest n such that this fails to be true. So if m is smaller, there must exist a coloring. Okay. Chromatic number of G is less than R of K, implies that there exists a partition of the vertex set into m pieces with m less than R of K, such that each UI is an independent set. Right? Again, I'm trying to read your faces, and I don't know if your faces mean, yes, yes, we already understand everything, why are you telling us? Or if your faces mean, what is he talking about? So try to, keep asking questions to let me know. Okay? So now we just use this coloring on these parts. Right, between ui and uj, every edge has the color between vertex I and vertex j. It's okay? Great. Okay, that was the warm-up. Now we have the real question. What is the Ramsey number of the path of length k? Yeah, of course. So we now sort of give color Cij to all edges between u and ui, and uj. Right. So we've given this coloring by the definition of R of k. Now we want to define a coloring of G, of the edges of G, without any monochromatic KK. This is the coloring. Because chromatic numbers at most are of K, then we can partition it into independent sets. So there's no edges inside. We just need to color the edges in between. And in between UI and UJ, we give every edge color Cij. I now claim there's no monochromatic KK. Why? If there was, it would have to have one vertex in K different parts, because they're independent sets. But then that would correspond to a monochromatic KK in C, which doesn't exist. So therefore, this is a coloring of the edges of G with no monochromatic KK. What it tells us, I erased it, sorry. What it tells us here, if you can, for those with photographic memory, that if the number of edges of G is less than R of k choose 2, then there's a coloring with no monochromatic KK. So the size Ramsey number is at least Ramsey number choose 2. Did it make sense this time? Great, thank you. Yeah, please do keep asking questions. Like I said, if you're all quiet, I'll assume you're understanding and skip on to the next thing. So, yeah. Okay, great. Okay, so, okay, let's prove some bounds on this thing. Who can give me a lower bound or an upper bound? Okay, I'm going to give you a lower bound. Maybe k minus 1. Let's not be too ambitious. Sorry, for me, pk has k. Sorry, for me, pk has k edges. I'm not doing Alex's version. Yeah, so for me, pk is a path of length k. And sorry? That would be very ambitious. For here. Yeah, 2k, very good. Sorry, yes, thank you. Yeah, color half and half. Yeah, excellent.
Upper bound,
Yeah.
2k minus 1 choose 2.
2k minus 1 choose 2. Very nice, because
We can, any coloring, we can cover all the vertices with 2 paths of different colors.
yes, this is so using some kind of fairly advanced fact from Ramsey theory. It is true that for every coloring, we can cover all the vertices with a red path and a blue path. Do you know how to prove this?
Yes.
Tell me.
Induction, you can do it without one vertex.
So you don't want them to be vertex disjoint. You just want them to cover. So maybe I drew it wrong. But yeah, maybe it's okay. Maybe it doesn't matter I drew it wrong. Yes, okay, that seems to work. So something stronger is true. You can even make the paths vertex disjoint. And here's the nice idea, if you know this one. You look for something that looks like this. And do induction with that. And when you add in a new vertex, you look at these edges. And then you can extend either the red one or the blue one. This is due to, I forgot who proved this first. Yeah, but this is the start of some very nice questions in Ramsey theory. People who like Ramsey theory, then this is, worth knowing about. Yes, anyway, so, yeah, we can get something, let me say something weaker. We can get something of like order k squared by doing some Ramsey theory. So by taking a sufficiently large clique, then you can find a monochromatic path inside the large clique. So our bounds are k and k squared. So Erdős asked a long time ago to prove, is it much smaller, is it much bigger? Do we want to take a bet? Who thinks that the lower bound is closer to the truth? Oh, let's say, okay, 3 possibilities, right? Lower bound, upper bound, and neither. Who votes for the lower bound being correct? We have a couple. Who votes for the upper bound being correct? A few. Who votes for somewhere in the middle? Lots of abstentions. Okay, it's roughly a draw between the 3. So the somewhat surprising fact, and I think this is surprising, it's the theorem of Beck, is that, the Ramsey number of the path is big OK. So the lower bound is correct. Okay. So, how are we going to prove this? Use a random graph. What a good idea. Yeah. Okay. So before we come to the random graph, I'm going to prove a lemma. The lemma has it's got a very beautiful proof, and it's a very useful lemma. It's worth knowing. It's completely extremal. So here is the lemma. Maybe due to Benelise and Kovalevich and Sudakov, I think. It says the following. So if the graph G is pk free, so has no path of length k, and then, let's say, then for all a plus b equals n minus k, there exist sets, so disjoint sets, I guess, disjoint sets A and B in the vertex of G such that size of A is A, size of B is B, and the number of edges between A and B is 0. So we can find these two large sets. We'll draw a path here. This is at most k vertices, A, B, with no edge between them. Okay, does the statement make sense? Okay, for any size we like, as long as it's not too big, right? Then we can find these two sets with no edges between them. I think a very strong property. Okay, let's prove it.
I have a question.
Yeah, please.
This part that's outside of A and B,
Yeah.
it's not necessarily a fact.
So yeah, you'll see in the proof that it is, but yeah, not in the statement. Yeah, yeah. So I drew it like that. Yeah, yeah. But thank you. Yeah, in the statement, no. Yeah. Yeah, this is perhaps a hint of what the proof looks like. So, how many computer scientists do we have in the class? Okay, so you guys have an advantage here. Tell me how to prove this. This is going to do something very familiar. We're going to use depth first search. Okay? Okay, so what are we going to do? We're going to do an algorithm that starts out with A being everything and B being nothing. And we also can have a path which at the start is empty. Okay? What we're going to do is we're going to pick a vertex of A to be the start of our depth first search. We're going to move it to the start of our path. Oops. And now we're going to go through these vertices one by one, asking whether there's an edge between them. We're going to look for edges until we find one. Suppose we find this edge. Then we're going to move this into the path. Right? This is just depth first search. Okay? And then we can do the same thing for this one. We're going to look, see if it has a neighbor in here, move the guy here, and continue. At some point, it has to stop. Right? Because we don't have a path of length k. This ends with this path having at most k edges. At which point, we move this guy into B. And we go back to this one, and we try again. If we find one, we move to P, and repeat with that guy. If we don't, move this vertex to B. We just keep doing this. In each step, we either move a vertex from A to the end of the path, or we move the last vertex into B. We continue until we've processed everybody. Okay? That's depth first search, seen in a slightly different way, maybe. Okay, now why are we done? Well, how many edges are there between A and B? We move a vertex into B exactly when it has no neighbors in A. So and then we just move vertices out of A. So there are no edges between A and B. Right? At all stages of the algorithm, there are no edges between A and B. And each step, we move one vertex from A into P, or one vertex from P into B. And that's all we do. So whichever value of A and B we want, we just wait till A has size A. And at that point, B must have size at least n minus A minus K, which is what we claimed. So we're done. Good. Everyone happy? You don't look happy enough. This proof is amazing. And it was computer science. Don't you think it's wonderful? It's like shocking. I was completely shocked when I first saw this, which is not that long ago. Yeah. Yeah. Okay? Okay, so we just run this process until we find our sets. That's it. Okay, so now let's use this lemma to prove this theorem. So, idea, use GNP So we only want to have a total number of edges being a constant times k. So we can only use a constant times k vertices, and we can only take p to be a constant over k. Right? If we do this, then we'll typically end up with about constant times k edges. Right? This implies number of edges of GMP, certainly the expected number is about Pn squared, which is what? It's like C cubed times k squared over k times k. Okay, which is fine. So the claim is, what's the claim supposed to be? GMP will not have these large sets. Right? But there's a catch. We're going to color GMP first, right? So we're going to take our graph G is going to be GMP. We're going to color it red and blue. And it's the red graph and the blue graph that are pk free. Okay, so what do we have? So we have a red graph GR and a blue graph GB. And they're both pk free. Right? Is it making sense? Do you know what's going on? We're taking this graph GMP. It's a random graph, right? So we don't know yet exactly what it is. We're still doing like a rough argument. But OK, so sample GMP, you get some random graph. We're going to color it red and blue. Our enemy is going to color it. So we're given these two graphs, the red graph and the blue graph. And we want to prove that there's a copy of pk in one of them, a path of length k in red or a path of length k in blue. So suppose not. Okay, so then we can apply this lemma to each one. So we get a set A and a set B with no red edges between them. And we get a set A and a set B with no blue edges between them. So what do we have? Here is our set A and B. This is at most k. No red edges. Let me do dotted red. Say no red edges. Or maybe I'll do them in red. Oh, sure. OK. And then there's also a partition. Not quite a partition, but two large sets in the blue graph. OK, so just losing 2k vertices, we have these sets where there's no red edges across this way and no blue edges across this way. Does that make sense? So, yeah, sure. Right. So, let's apply the lemma to the red graph. Maybe I'll draw it in red to make it clear what it is. So, there are no red edges between these two sets. There's a set of size at most k here we have to throw away. This is a partition of all the vertices. And we can choose A and B as we like. So we can choose it to be n minus k over 2 and n minus k over 2. And n is much bigger than k. It's like 100k. Okay? So this is like basically n over 2. Right? Does it make sense now? There's no red edges between these two red rectangles. And I'm doing the same thing with the blue graph, which is also pk free. So it's going to be a different set. So some of these vertices are going to come up here, but it's still just a small set. And then what's left is going to be partitioned into two sets, again, both of size n minus k over 2. So okay, maybe we've thrown away these, so maybe it's n over 2 minus, I don't know, 3k or something, whatever. Right? Each of these sets has size almost n over 2, just throwing away a little bit. And there's no blue edges between the two blue rectangles by the lemma. Those are the sets A and B given by the lemma applied to the blue graph. It's okay? Right. Now, how many edges are there between this set here and this set here? 0. There's no red edges and no blue edges. And similarly, how many edges are there between this one and this one? 0. I claim that either both these sets must be big, size, let's say, n over 8, or both of these must be big, at least size n over 8. Let's check that. Suppose these were both, what am I saying? So one of these two was small. Let's say this one is small. Small. Well, this blue rectangle is big, so this one's big. And this red rectangle is big, so this one's big. Right? So if any one of these is small, it means the other two, the diagonal to it, are big. So what have we found? We found two very large sets, size n over 8, with no edges between them at all. Is it clear? So, if we can show that GMP does not have two large sets with no edges between them, then we're done. All we need, what we've shown is any graph in which every two large sets have an edge between them. When you two-color, you find a monochromatic path. Right. Okay, so the final thing to say in this proof is I'll do it over here. So lemma. So with high probability, if P is at least a constant over n, then every A and B in the vertex set of GMP, say, with A and B at least n over 8, say, there exists an edge. I'm going to say EAB is bigger than 0. Okay, so I claim that the GMP has this property. If you take two very large sets, there's always at least one edge between them. Proof. Just the same thing we've been doing the whole time, right? We want to know if there's one of these pairs of sets, count them, right? Proof. X equals the number of such sets A and B, and look at the expectation of X. What is the expectation of X? Excuse me. It's the most what? How many choices for A? At most 2 to the n. Let's be silly. How many choices for B? Also almost 2 to the n. And what's the probability there's no edges between A and B? 1 minus p to the power size of A times size of B. They're at least n over 8, so n squared over 64. Right? Choose A, choose B. What's probably there's no edges between them. This is at most 4 to the n e to the minus pn squared over 64. But p is at least some large constant over n. This is at most 4 to the n e to the minus c over 64 times n. If c is large, c over 64 is also large, then this beats this. This tends to 0. Right? So the expected number of such pairs is small, so with high probability, there's none. Just the same thing we've done like more than 10 times now. Maybe 15 times, I don't know. Right? Okay, so GMP does have this property. And because it has this property, it tells us that this cannot happen. And therefore, this two-coloring, these graphs cannot both be pk-free. Either red or blue has to have a copy of a path of length k. Did it make sense? You stopped asking questions, which probably means that you are lost, unfortunately. Is it okay? Happy? Good. Some people happy, some people not happy. Okay. Great. So the reason I wanted to show you this, apart from the fact that this is very beautiful, is that this is a very first example of a very sort of fundamental technique in probabilistic combinatorics and the study of random graphs. This is what's called a pseudo-random property. Right? So you may have come across pseudo-randomness in other contexts. You see, this is just some deterministic property of a graph. Right? This is a pseudo-random property. So a pseudo-random graph is a graph that has some property that makes it look a bit random-like. And here, what is the pseudo-random property? It's that every large pair of sets has an edge between them. There are edges everywhere. Right? And this lemma is just saying GMP has this pseudo-random property. And the proof was, if there exists a pseudo-random graph, then that one is good. There's the 2 steps, but it's a very useful technique. Prove that GMP has certain pseudo-random properties with high probability. So you have a pseudo-random graph. The pseudo-random graph gives you what you want. Right. Okay. There's only 5 minutes left, so I'm probably not going to start a new topic. Yeah, what can I say? Yeah, I think I won't say anything. So yeah, let's finish it today, and then tomorrow, yeah, I'll do some of the more advanced things I wanted to do. If you want to vote on which ones I should do, or if you don't know what they are. Maybe you don't know what they are, so it doesn't make any difference. Okay, yeah, I'll pick something. Okay.